Our next speaker is Michael Kim. Michael just completed his PhD at the Stanford Theory Group, and he's currently a UC Berkeley Miller postdoctoral fellow. Michael.
Great. I'll wait for the slide. Great, so we can go to the next slide. Thanks. So these days, predictive algorithms are everywhere we look. They drive our cars and our economies. They're making medical predictions and even sometimes telling us who we should get married to. And really, algorithms are increasingly used to make consequential decisions about people and are having a profound impact on our daily lives. And while such predictive algorithms have the potential to yield great benefits to society, unfortunately, for every amazing algorithmic achievement you hear about, you also see, like on the next slide, headlines highlighting the bias and unfair discrimination that can be baked into these predictive algorithms. On the next slide, we discuss a specific issue that came into focus recently in the California elections, where Prop 25 gave voters a choice to eliminate cash bail and replace it with a certain risk assessment algorithm. Now, cash bail has long been understood to discriminate against people on the basis of race and socioeconomics. But critics of the proposition, like the ACLU of SoCal, worried that the risk assessment algorithm would exhibit exactly the same issues of bias and unfair discrimination as cash bail itself. And so amidst lots of concern about bias in prediction systems, it's actually quite easy to identify examples where the algorithms we're using are behaving in a manner that somehow we feel is unfair, but devising an effective strategy for mitigating this algorithmic unfairness is a bit more challenging. And that's where my research begins. We'll talk about it on the next slide. So rather than addressing each example of bias as we see it on the fly, my research tries to take a more foundational approach, identifying general patterns of unfair algorithmic behavior, and then translating these patterns into formal notions of fairness in the language of theoretical computer science. And really a large focus of the research is on making sure that we have the right definitions, where we need to balance the desire for general purpose solutions, as well as an awareness for the context in which the notions will be applied. And ideally, developing these definitions will really help us to understand what we can and cannot expect from machine-learned predictions in a given context. The eventual goal of the research program is to develop efficient machine learning that comes with a provable guarantee of fairness properties, much in the same way that modern cryptography provides us in our browser with a provable certificate of security in our online transactions. On the next slide, I want to give you a flavor of the type of definitions that we work with. So the main notion that we've been studying for the past few years is called multicalibration. Multicalibration says that predictions should appear calibrated, not just overall, but on every subpopulation that can be identified within some computationally bounded class of subpopulations. We show that the guarantees of multicalibration are significantly stronger than the corresponding guarantees of group fairness, and we give algorithms that reduce the problem of learning a multicalibrated predictor to standard machine learning tasks, showing its feasibility. So finally, on the last slide, I want to conclude with a preview of some hot off the press work, where we start with a really simple idea. And the idea is that perhaps fair predictions should somehow be indistinguishable from a set of ideal predictions. Now, you have to be careful about exactly how you make this intuition rigorous, but it leads us to a certain notion that we call outcome indistinguishability. The framework outcome indistinguishability for reasoning about predictions turns out to be very general, even more general than multicalibration, and sets up a number of interesting questions about learning and prediction that we're excited to dig into further. Thanks a lot.